Hello, we're going to look at gravitational fields just a little bit more. All right. So what I got here are three pictures. We got the sun. It's red because it's hot. It's a ball of fire. We got the earth, which is blue because it's the blue planet, right? Because of all the water. And we've got the moon, which is black because it's just boring and gray. All right. So what I'd like us to do just really quick is draw in some gravitational fields to show the influence of those objects. All right. Now we are going to just kind of pretend that they're on their own. Okay. We're not doing the attractions between them right now. We're just drawing the gravitational field around each one. All right. Now the moon is the smallest, right? It has the lowest mass, which means it's going to have the weakest gravitational field. And so I'm just going to draw maybe 4 lines going in to the moon, just like that, the gravitational field of the moon. So you can see that no matter where I put my mass, remember we had our yellow mass, we put the mass here, and it's going to go whoosh, and it's going to be attracted, right? That's the theory of gravitational fields, is just that they exert this influence, right? If we move on to the Earth, we know that the Earth is a bit bigger, right? Now, we're not going to do it proportional just because it would take way too many lines when we get to the sun. But just to kind of give an idea, we recognize that the Earth needs to be stronger than the field of the moon. So I'm going to put in maybe, let's throw in like 12 of these guys. All right, so here we go. Boop, boop. Just like that. And so those lines are representing the gravitational field of the Earth. So recognizing that because these are a little bit closer together, the field of the Earth is going to be stronger than the field of the moon at its surface. All right. Another thing you want to recognize is that at the surface, the lines are always perpendicular, right? The lines are always perpendicular to the surface there. That's one thing we want to pay attention to when we're drawing fields of any kind. But you can look at this and say, oh yeah, there's a lot more lines close together there. This must be a stronger gravitational field. All right, now we're going to move on to the sun, our big red ball of fire over here. And we say, oh, well, the sun is really, really big. So therefore, it's going to have an even stronger gravitational field, right? It has the ability to have a larger influence over something that comes in that field. And so we're going to just have a lot more lines here coming in. And of course, these extend all the way out. I'm being a little bit lazy just because I want to make sure I don't run out of time here. Again, they should be perpendicular to the surface. They should be more or less evenly spaced out. And hopefully this kind of gives you an idea. You look and you look at the sun here and you say, oh, wow, look at all those lines going into the sun. They're really close together. Therefore, the gravitational field must be really, really strong on the surface of the sun. Surface, you know, we know it's not a solid ball, but, you know, at the surface, it's going to have a much stronger gravitational field there. So this kind of helps us, again, visualize that idea of the gravitational field. But we haven't really talked about the math of the gravitational field yet, right? We talked about Newton's law of gravitation, which was Fg equals the gravitational constant. This is not the same as that little g, by the way. Hopefully you've gotten that by this point, but this is not the same as that. That's why it's a capital. This is Newton's constant of gravitation there. And then times m1, m2 over r squared, right? Where those are the masses of the objects and r is the distance between them. So we talked about the force between two objects, but that really doesn't give me a value for the strength of the field of this object, right? It just says, well, if I put another object here, now I have mass 1 and mass 2, and I can find the force between them. But when we're talking about fields, we don't want to have to pay attention to this guy. We want to get rid of this guy. We want to take this force, and we want to divide by that mass. Oh, get out of here. All right, so we want to divide that mass out of the question. So that's what we're going to do. We're going to divide by one of these masses here. All right, now it really doesn't matter which one of those is this mass and which one of those is this mass. But the one that's left, the mass that's left, is we're going to take this and we're going to divide by the mass of the guy that we just took out. Okay, because we want to know what is this guy's influence even when I don't have a mass there. When that mass is gone, what is the influence or what is the possible influence of my object? So we divide that mass out. And so what we get when we divide the force by the mass is we get the gravitational field. Now, some of you are thinking, yeah, but isn't F equals ma? So if I divide by m, don't I get the acceleration or the acceleration due to gravity? Yes. In fact, that's what we've been calling the gravitational field all year long, is the acceleration of gravity. But that's exactly right. We get the gravitational field is equal to, and then we've still got the big G. We're left with one of those masses, the mass that's creating the field here, all over r squared. This guy canceled out when I divided out that extra mass. And so what we're left with, we're left with now an equation that allows us to get the strength of the gravitational field just due to the mass of that object. Now, obviously, depending on where I am, that field will be stronger or weaker. If I'm here, the lines are close together, that should be a lower radius, and so I should have a larger field. If I move farther out, then the lines are further apart, which means I should have a weaker gravitational field, which makes sense. If I have a larger number on the bottom, I divide by a larger number, I should get a smaller number here. But you'll notice that this equation right here, the gravitational field equation here, does not depend on a second mass. This gravitational field is just the field strength being created by this mass. I can do that with any of these. You can have the mass of the moon be there, and you can find out the strength of the gravitational field there. I can put the mass of the sun there, and I can find out the strength of the gravitational field of the sun. Now, of course, if I do want to know the force on another object, then I can bring the other mass back in, and I can calculate that. And of course, that comes from, if I take the gravitational field and I multiply by the new mass, then I get, again, the force of gravity, which is what we've been doing all along. We've been saying, oh, the gravitational field of the Earth is 9.81 meters per second squared. Multiply that by the mass, and we get the force of gravity on the object at the surface of Earth, or the weight. All right. The thing to recognize now is that we now have a way to do it anywhere, not just at the surface of Earth, not just on the surface of Mars. We can now, by knowing the mass of that object and how far we are, remember, this is how far we are from the center of the object, we can now figure out what the gravitational field is, or in other words, the gravitational acceleration. And from that, we can calculate the force if we would like to do so. So this is the idea of gravitational fields. And hopefully that will help you as you go forward and as we start to look at electrical fields and magnetic fields. All right, that's it for today. Good luck. I'll see you next time.